Okay, so we're going to talk about the kinetics of radioactive decay, all right? And what we're talking about, of course, when we're talking about decay, we're talking about basically starting off with a radioactive nucleus, and it basically emits some particle. Could be an alpha particle, could be a beta or gamma rays or, whatever, all right? So what you'll find is that for all types of nuclear decay, they all follow a first order process, all right? So basically all nuclear decay is a first order reaction. So there's no such thing as a zero order or a second order nuclear reaction. All of them are first order reaction. What that means is that if you take the rate of the decay as being equal to minus the change in the number of nuclei over the change in time, then that can also be equal to this equation right here, which is the rate of the reaction is equal to lambda times n. Now, let me just explain what those two terms mean. N is the number of atoms or nuclei at time t, right? And, oops, right. And lambda is what is called the decay constant, right? It's kind of similar to the rate constant that we met before when it comes to kinetics, chemical kinetics, right? So what this is saying is that the rate of the reaction, the rate of the nuclear decay, is equal to the decay constant times the number of nuclei. So because rate is equal to this and rate is equal to this, we can set these to be equal to each other. And then through several steps involving calculus, we're going to end up with this equation and this equation. And these should look somewhat familiar because these are very similar to what we saw in the case of first order kinetic reactions, all right? So in this case, what this is saying is that the number of nuclei remaining is equal to the initial number of nuclei times e to the minus lambda t, right? And then basically if we find a natural log of both sides, we end up with this equation right here, all right? Another thing I need to introduce to you, which again should look somewhat familiar, is the concept of half-life. If you remember, we said that the half-life of a reaction, first order, is equal to the natural log over the rate constant. That's for chemical reactions that are first order. In the case of nuclear reactions or nuclear decay, a similar equation can be expressed for the half-life. The half-life is equal to ln2 over the decay constant, all right? So that's basically how we can determine the half-life. And the half-life has the same meaning as we discussed in chemical kinetics. It's a time taken for half the initial amount of the, in this case, nuclei to decrease by 2, or half of it to react, let's put it that way, all right? So that's basically all you need to know in terms of the equations for the kinetics concerning radioactive decay, right? Now, going back up here, lambda times n, the decay constant times the number of nuclei, that combination is called the activity, right? And that activity can be measured directly. But before we get into how that is measured directly, as a result of the fact that lambda n is equal to activity, we can have other forms of this equation depending on what you're trying to calculate. So for example, this equation here can be expressed as activity at time t is equal to the initial activity times e to the minus lambda t, all right? And this here can be natural log of activity is equal to the natural log of the initial activity minus lambda t. And the reason why we can say that is because the activity is directly proportional to the number of nuclei, because remember, lambda is a constant, right? So basically, because of the proportional relationship between activity and the number of nuclei, then we can write these equations right here, based on these equations up here, right? And that's not only true for activity, that's true for mass, anything that is proportional to the number of nuclei. We can insert those terms into these equations, all right? And we're gonna see in the assignment a couple of examples of that. So let's talk about how do we measure, before we get to measuring. So this is just basically a graphical plots of, in this case, the number of nuclei present at time t versus t. And of course, you see there's a fall off as time progresses. The number of nuclei remaining would decrease. And of course, given this function right here, you should know from your math that this line will be approaching t but won't touch it, right? On the other hand, this is more useful because when you plot the natural log of the number of nuclei present versus t, you're going to get a straight line graph with a negative slope, and that negative slope will give you the rate constant, right? So if you want to find a rate constant for a reaction or a radioactive decay more specifically, then just find the slope of this. And also, if you need to find a half-life, as we said before, half-life is equal to ln2 over lambda. So once you find lambda, then you can find the half-life of the reaction. Okay. So as I was saying, how do we actually measure activity? Well, this here is a simplified diagram of what is called a Geiger-Müller counter. And basically how this works is that you have this cylindrical can right here. The metal, I don't remember what it's made of, but it's a metal. And that serves as a cathode. And there's an inner metallic tube here which serves as an anode. So they're both connected to a high voltage source, and they're also connected to an amplifier. And inside this can, you have argon gas, right? And you have a window here, which you point that window to whatever the radioactive source is. And what happens is that the radiation will pass through the glass and ionize the argon gas. So the argon gas will be an ion, the atoms will be converted to an ion, and the ion will be attracted to any one of these electrodes. Well, in the case of argon, it would be the negative electrode, which would be the cathode, because the argon would be converted to a cation. So it would be converted to the cation and then attracted to the cathode. So each time that ionization takes place, the counter here registers, right? So basically the total count that will be registered on the counter after amplification of the symbol, of the signal, then you're going to end up with a reading, and that would represent the activity of that particular material that you're trying to measure the radioactivity of, all right? And that's basically how this works, right? Okay, so let's talk about some applications of what we just talked about in terms of determining the activity of different substances. One thing you can do with this is what we call radiocarbon dating. And in fact, you have different types of dating of artifacts, you know, something that you might, you know, dig up at an archaeological site. And let's say you want to find out the age of a particular artifact, then this basically is useful for that. And carbon is not the only element or isotope. Carbon-14 is not the only isotope that is used for this purpose. There are some others, but we're just going to stick to radiocarbon dating. There are some limitations. In fact, one limitation is stated right here, and that is that this works only for objects that are more than 50,000 years old, right? So for objects that are younger or less old, this doesn't work too well. So the basis of this particular approach in terms of determining the age of an object, an artifact, is the fact that, okay, these two reactions are always taking place on Earth, and I would say maybe in the universe, but definitely on Earth. You have the conversion of nitrogen-14 to carbon-14 by bombardment of the nitrogen-14 nucleus with neutrons. So you're going to end up with carbon-14, and you're going to end up with protons. And then after that, the carbon-14 itself will undergo decay, beta decay, to reform nitrogen-14. So basically you have these two reactions taking place, and the consequence of that is that the amount of carbon on Earth remains pretty much the same, because as soon as carbon-14 is used up or produced, it's used up, right? So the level of carbon-14 on Earth remains the same as a result of these two reactions. The carbon-14 itself will eventually be incorporated into carbon dioxide, right? So some of the carbon dioxide that is present will have carbon-14 in it. And of course, living organisms will have a certain amount of carbon-14 as well, because carbon dioxide, by the way of photosynthesis, I'm quite sure you're all familiar with that, will absorb carbon dioxide, which again contains some carbon-14. And then what happens is that animals, such as human beings and so on, will consume these plants. So of course, we will have carbon-14 in our bodies as well, right? Now, stated here, when an organism dies, what happens is that it's not absorbing any more carbon dioxide, right? So as a result, the carbon 14 levels fall as a result of the second reaction that we just talked about here, the beta decay, right? So basically, what we can do is compare the activity of the living organism in terms of carbon 14 emission, and then the activity after the organism has died and some time has passed. And based on those two, using the equations that we just discussed, we can determine the age of the particular organism or artifact or whatever we're trying to determine the age of, right? Key to this is knowing what the half-life of carbon 14 is. And the half-life of carbon 14 is given right here, 5,730 years, all right? So that's basically how we can determine the age of an artifact. So let us look at, let me bring up the assignment again. Question number 21, all right? So we'll go here. This is assignment number 8, right? Oh, by the way, have you guys tried the other problems, balancing equations, nuclear equations? Any issues with them? Any issues? Anyone you want us to discuss? No? Okay. So let's look at question number 21. It says, a piece of wood from an ancient artifact has a carbon 14 activity of 11.7 disintegrations per minute per gram of carbon. Current carbon 14 activity in fresh samples is 15.3 disintegrations per minute per grams of carbon. And it gives you the half-life of carbon 14. This should be 14 right here. Please make a note that that should be 14 right here, right? Carbon 14 is 5,030 years. Calculate the age of the wood. So the equation we're going to use to solve this is the equation that we met before, which is ln A over A0 is equal to minus KT, right? So remember, A is the activity at the current time, A0 is the initial activity. Oh, by the way, I keep using K, it should be lambda, not K. K is for chemical reactions, lambda is for nuclear reactions. Okay, so as I was saying, A is the activity at the current time, A0 is the initial activity, lambda is a decay constant, and T is the time. So T is what we're trying to find. T is equal to minus 1 over lambda times ln A over A0. All right, so we know what A is. They gave us A, which is equal to 11.7 disintegrations per minute per gram. And A0 is 15.3 disintegrations per minute per grams of carbon. So the only issue now is what is lambda. They didn't give us lambda, but they gave us the half-life, right? And remember, the relationship between half-life and lambda is equal to ln2 over the half-life. All right? So let's do that first. ln2 divided by 5730. And the units for this is years, right? So 2 natural log divided by 5730. And according to my calculation, this works out to be 1.21 times 10 to the minus 4. And the units here would be years to the minus 1, right? So basically, we just put this value here where lambda is. So you're going to end up with minus 1 over 1.21 times 10 to the minus 4, years to the minus 1, times the natural log of A, which is 11.7 disintegrations per minute per gram divided by A0, which is 15.3 per minute per gram. And that's it. So let's see what this gives. So 11.7 divided by 15.3. And then I find a natural log of that. And then I'm going to divide by minus 1.21 times 10 to the minus 4. And according to my calculation, when rounded off to 3 sig figs, the answer is 2,220 years. That's according to my calculation, all right? So that would be the age of the particular artifact. All right? Any questions about this? Any questions? Any questions?
2,200?
2,220, yeah. Rounded off to 3 sig figs. All right? Okay, so that's number 21. I take it it's okay for me to clear this, right? All right, let me clear this. Let's scroll down to question number. Okay, now this one is not a radio, not a dating question. It gives you the half-life of a particular nucleus, right? It says it's 3.88 days, and the question is asking how many milligrams of a 5,000 milligram sample of radon 222 remains after 60 days. All right. I think there is another typo here. Let's add a decimal point to the 5,000 here to make that 4 sig figs. All right. So the question is asking for the half-life, right? And the equation we're going to use is, again, ln ln of the activity over activity initial equals to minus KT, right? Actually, the other form would be more useful. Well, a couple of things. The other form would be more useful, but not only that, they gave us the mass. They did not give us the activity, but the mass is proportional to the activity, right? So basically what we can do is replace A with M at the time T and A0 with M0, which is the mass initially, which is the 5,000 milligrams here. So the form of the equation I would use is M is equal to M0 times E to the minus lambda T, right? So M0 would be the 5,000 milligram times E to the minus lambda T. Now, they did not give us lambda, right? So how would you find lambda? Anybody? They did not give us lambda, but they gave us something else.
Lambda equals natural log 2 divided by half-life.
Exactly. And the half-life is?
3.88 days.
3.88 days, exactly. So let's work out that first. 2 natural log divided by 3.88. And according to my calculations, I got 0.179. Please correct me if I'm wrong. Oops. 0.179 days to the minus 1, all right? So that lambda will go here, 0.179 days to the minus 1, and then I'll multiply that by the time. 60 days. I'm going to assume that is 2 sig figs. So let's see what that gives. So put this in parentheses here. All right, so 0.179 times 60, and then I put a minus sign in front of that, and then I do that, multiply by 5,000. And according to my calculation, this works out to be equal to 0.1083 milligrams. And that's how that is done. Okay, any questions about this one? Any questions?
For the lambda and the time,
Mhm.
like, do they have to have the same
Units.
units? Yeah.
Mhm.
Okay.
Or at least the units should be able to cancel out. In this case, it just so happens that you have days here and days to the -1. Now, if they have given you something like years or something like that, you'd have to do some conversion in order to make sure that the units are compatible so you can cancel them out. All right? Okay, any other questions about this? Oh, yes, sir.
About the significant figures when it's e to the minus lambda times t, do those not affect the significant figures?
Yeah, it will. I didn't show the steps, but it will. But if you do that, 0.179 times 60, you're gonna get that. You're gonna get this part here, you're gonna get 11 because you have to round off. I'm assuming that this is 2 sig figs. And then when you do that, let me see what you get. Okay, what did I do wrong? Okay, it looks like you get a different answer here. So when I rounded off this to 2 sig figs, and then let me do this one more time just to make sure, because okay, so when I redid that, I got 0.08351. Okay. So that would be the answer for that part. Okay. Any other questions? Any other questions before we move on? All right, so let's continue. Let me clear this first. Scroll down. Okay, this one says, what is the original mass of C14 in a sample of if 10 milligrams remains after 20,000 years? And again, it gives you the half-life of carbon-14. All right, so again, the form of the equation I would use is M is equal to M0 times e to the minus lambda t. Now this time, the question is asking for the original mass. So therefore, this would be, when rearranged, you're going to get M0 is equal to M e to the lambda t. So M at the time t is 10.00 milligrams. Multiplied by e to the lambda. Now lambda, we don't know what that is, but we calculated lambda earlier because we know that lambda is equal to ln2 over the half-life. And what was lambda that we calculated earlier? 1.21 times 10 to the minus 4 years to the minus 1. So that goes here, 1.21 times 10 to the 4 years to the minus 1, multiplied by t. And t is 20,000 years. All right. So again, I'm going to assume that is, in this case, 5 sig figs. So let's see what this gives. 2,000, or actually 20,000 times 1.21 times 10 to the minus 4. And then I do shift. And then, okay, hold on. Okay, so this part here works out to 2.42. All right, this part right here. So I'm going to now do E to that number. And then multiply by 10. And according to my calculation, this works out to be equal to 4 sig fig, so 112.5 milligrams. That's what I got. Right? So that's basically how that works out. Okay, any questions about this? Any questions? Yes, sir.
Last question, was the units gonna be in milligrams too?
Number 22? Yeah. Yeah. Okay, any other questions about this one? Number 23? Okay, let me clear this. Scroll down. Okay, oh, we did this already. At least we started. If I remember correctly, I did number 24 for you, right? And I told you guys to try 25, 26. And that's basically it for this assignment, right?
For 24 though,
Oh, okay, yeah.
like when you did A, you just get to C. Like you found the binding energy per nucleon. But you use the mass defect over the number of nucleus before finding the binding energy.
Oh, okay, so the binding energy,
Like we saw the A and then you skip to C.
oh, I did?
Use the value from A
Oh, okay, hold on.
for sure.
I found the mass defect first, right?
Mhm.
Let me see if I have it here.
You did, you just didn't scroll down, you did it above it.
Oh, okay. Because the mass defect, okay, so if I remember correctly, the mass defect I calculated was what, 9.106 times 10 to the minus 3? What did I get?
8.478 ME volts.
All right, let me redo this one again just to be sure. So just to remind you,
If you put the value from here over, it should have been, you have to solve binding energy.
Isn't that binding energy?
No, this is the mass defect.
okay, so just to remind you,
So like,
we're looking at the complete breaking up of the tritium nucleus into its constituent particles, right? So the atomic number is 1, so we know that there's 1 proton present, and the mass number is 3, so we have 2 neutrons present, right? So delta M would be equal to the sum of the masses of the protons and neutrons. So the mass of the proton is 1.007825 AMU plus 2 times the mass of the neutron, which is 1.008665 AMU, all right? And then after adding that, we're going to subtract from that the mass of the tritium nucleus, which is 3.0160,490 AMU, all right? So let's see what we get when we add this here. So 2 times 1.008665. To that, I'm going to add 1.007825. And this part here ends up being equal to 3.025155 AMU. And we're going to subtract from that 3.0160,490 AMU. So let's see what that gives. So that minus 3.0160,490 AMU. So I got, so this is probably where I made the error if what you're telling me is true. I got 9.106 times 10 to the minus 3.
yeah, but then you convert it to the megavolts.
Oh, okay, all right, I got, okay.
So we got that, yeah.
Okay, so okay, so what you're saying is that what you just said is the answer to this question right here. Because
So that is the.
exactly, so basically to get the binding energy, that's where you multiply the 9.106 times 10 to the minus 3 by AMU by what was it, 931, okay, 931 mega electron volts over 1 AMU. Right?
You did all that in part A.
Oh, okay, my bad, okay. So yes, so when I did that, let me see what that gives. So multiply by 931. So I got, rounded off to 4 figs, I got 8.478. That's what I got, right?
Yeah.
Mega electron volts, okay, fine. And that's it. And then to answer the next question, which is the binding energy per nucleon, which is the C part. Basically, you take this value here and divide it by the total number of nucleons, which in the case of tritium is 3. So the binding energy per nucleon is equal to 8.478 AMU divided by 3 nucleons. And that is equal to, so 8 divided by 3. So I got, rounded off to 3 sig figs, 2.826, 2.826 AMU per nucleon.
Would it be ME?
Hmm?
Instead of AMU, it'd be mega electron volts.
I'm sorry, mega electron volts. Yeah, you're right. My bad. Okay, and that's, oh, that is done. Yes, ma'am.
2.4.
Well, that's what I got now. So let me redo this just to be sure. 8.478 divided by 3, 2.826. I don't know, maybe I slipped on that. Should have slided
And then,
before.
like, where do you get the number of nucleus? Like, do you tell
Right,
us
so
the equation?
the nucleons are all the particles present in the nucleus of the element, right? So therefore you have two neutrons and 1 proton, so that's 3. So that's where you get that number from, the number of nucleons. 2.8. I hate to hear myself talk, so
What was the units for 2.826?
mega electron volts across this out here. Mega electron volts per nucleons. Yeah. Okay, any other questions about this one? And pretty much it's the same process. The numbers are going to be different, of course. It's the same process for the others below. All right, same process. Okay, so let me see what is left in the, can I clear this? All right, let me see what's left in the PowerPoint plus discuss, because that's the last question. Okay, let me just go through this. This is basically talking about some applications of nuclear reactions, all right? One is called nuclear transmutations, right? So I know it's true in medicine, and I'm quite sure it's true in other fields. There are some techniques, some procedures, some instrumentations where nuclear isotopes, radioactive isotopes are required, right? So somebody has to make them, right? And there are companies involved in manufacturing these radioisotopes, right? So this is just showing you how one particular isotope is being made. It's called nuclear transmutation. Basically what that means is that you're transforming one isotope to another, usually by bombarding a more stable isotope to form one that is more reactive, right? So in this particular case, we're making the oxygen-17 isotope, which is not stable, so it's radioactive, but we're creating that out of nitrogen-14, which is more stable, right? So in this particular case, oh, and there's another example as well, the transformation of aluminum-27, which is again a stable isotope being converted into phosphorus-30, which is not as stable, right? So basically, what is used, oh, and there's the fourth one or third one, again, creating a less stable isotope from something more stable. Now, what they all have in common is that in order for this reaction to work, or these reactions to work, the smaller particles must be moving at a very fast speed to hit the more stable nuclei, and then the energy from that allows for the formation of the less stable nuclei. So how do we achieve those particles moving at very fast speed? Well, what we do, or what they do, is that they have two magnets that are, I should say two electromagnets, right? That have an alternating voltage system. So basically at one instant, one pole of the magnet would be, I'm sorry, not magnet, what's the term? Oh gosh, I forgot the term. But they call them Ds, right? Because they're shaped in a Ds, but it's not magnet. It generates an electrical force or electrical field, right? So what happens is that you have your particles located here, and let's say you're dealing with an alpha particle, right? The alpha particle is positive. So at one instant, this is negatively charged. So what will happen is that the alpha particle will move into the D here, which is negatively charged because it's attracted to it. And then immediately there's a switch where this becomes positive and this D becomes negative. So because this becomes positive, it starts being repelled into the other D, which is more negative. And then there's a switch again where this becomes positive and that becomes negative. And again, you're going to have the alpha particle moving from this to this, and that continues over and over again. And while that is happening, the particle, in this case, the alpha particle, is moving in wider circles, right? And by the time it emerges from here to hit your stable nucleus here, it will be moving at a very fast speed, right? And therefore the reaction will take place, and then you're going to end up with the required or desired nucleus being produced, right? So this is basically what is employed when it comes to making these particular radioactive isotopes, because you cannot just get them naturally from any natural source. You have to create them, and this is basically what is done, all right? So these are just some examples of different nuclei that are created in the method that I just described. And what they all have in common, of course, is that you're starting from a more stable isotope to something that is more reactive or more radioactive, all right? Another thing I want to talk about here is what is called nuclear fission, all right? And basically what happens in the case of nuclear fission is that you have a relatively large nucleus, you bombard it with a smaller particle like a neutron or alpha particle, and then what results is that the large nucleus is broken up into two smaller fragments, and you may have some other smaller particles being produced in the process, right? So this is the equation for this reaction here, right? And of course, you see that there's a large amount of energy that is produced. In fact, you can calculate the amount of energy by using the same formula that we did, that we used earlier to determine the binding energy and the mass defect and so on. So in this particular case, what we do is that, and I just realized there's an error here. This side should be over here, and this should be over here. So let me just make a note of that. So basically what you do is take the mass of the products, right? Which would be the strontium, the xenon, and the 3 neutrons here. And you're going to subtract from that whatever is on the left side, which would be the mass of the uranium and the 1 neutron, right? So please make a note of this. You should switch these two, right? Because remember, it's always products minus reactant, right? And then after you find that mass defect, so to speak, then you multiply by the speed of light squared, and that would give you the energy that in this case would be released, right? So it turns out that when you put the numbers in and you do your calculation, it turns out that the energy that is released per nucleus of uranium is 3.3 times 10 to the minus 11 joules. Now, if you were to extend that to per mole, 1 mole of uranium-235 is about 235 grams. So therefore, what you'll find is that the amount of energy released is 2.0 times 10 to the 30. Now, to compare that to some other energy source like coal, what you see is that when you burn 1 ton of coal, the amount of energy released is 5 times 10 to the 7 joules, right? So you can see when you compare these two that the amount of energy that's released for 235 grams of uranium is much more larger than what you get when it comes to burning coal, right? And that's the reason why nuclear fission and this type of reaction is seen as a more beneficial alternative to burning coal. There are other aspects to, of course, consider, for example, pollution and so on, right? But if you just look at the numbers in terms of the amount of energy released, comparatively speaking, nuclear reactions wins out in terms of efficiency, all right? So let's talk about nuclear fission in more detail. I want to talk about the nuclear chain reaction that will take place in the reaction that I just described. So if you remember what we just saw, you're going to have a neutron hitting the uranium-235 nucleus, and then you're going to get some products, one of which would be the neutrons, the 3 neutrons, right, being produced, right? So potentially these 3 neutrons can go ahead and contact and collide with other uranium-235 nuclei to basically continue the chain of reaction. But the chain will not continue if you don't have enough of the uranium-235 present, right? So if the mass of the uranium-235 is too small, then after a time the reaction will stop. But if the mass is at what we call a critical mass, then what will happen is that you're going to have a self-sustaining nuclear chain reaction continuing, right? And basically when it comes to nuclear power plants, you have to basically have a handle on, this chain reaction, because if it gets too out of control, then as you can imagine, it wouldn't be a nice experience in terms of explosions and so on. So this is controlled, and I'm going to show you a diagram where it shows you how that is done, right? But the important point here is that the critical mass, right? In order for the chain reaction to continue, then you must have at least a minimum amount of the material that would allow for that chain reaction. If the mass is too small, then after a certain number of collisions between the neutron and the remaining 235 uranium, then the reaction will stop, all right? So this is a diagram which basically shows you how the nuclear reactor works based on the reaction that we just discussed. There was one nuclear reactor that Duke Energy had in Crystal River. And I remember when I first started working here, I was planning on taking students to a trip there so that they can see it works, only to find out that they started to decommission that particular plant shortly after I got here. So unfortunately, we didn't get to have the chance to have that tour. Anyway, so basically this is where the reaction takes place, right? The uranium fuel rods are represented by these red colored rods right here. And the green rods are basically carbon. Carbon is used basically to control the flow of neutrons. So basically, if you want to slow down the reaction rate, then you basically push the carbon rods down. If you want to increase the rate, then you put it back up. And basically what will happen is that the reaction here will generate heat energy, which will be fed. I think the liquid that is used to transport the energy in these pipes is water. And then you have this big tank here, which has water again. So basically, the heat is transferred to the water in this big tank. The water here is vaporized, and then this is led to a steam turbine, which produces or converts the heat energy into electrical energy, and then that is fed into the what do you call it, the network or circuit or whatever that basically serves the public, right? So that's basically how this works, all right? And this is just a picture here showing you the actual reactor. Okay, so again, when you compare hydrocarbon sources of energy compared to nuclear energy in terms of the amount of energy per waste produced, that's what we're looking at here. What you'll find is that the nuclear power plants will generate less waste compared to coal-fired plants. And this is just a solid waste. In addition, you have gases being emitted, sulfur dioxide, carbon dioxide, and so on, right? So again, when you compare nuclear source of energy compared to hydrocarbon sources, in terms of the amount of waste generated, nuclear sources would be better. But there is a problem. There's no free lunch when it comes to these things. And that is that the waste itself, even though it's small compared to, in the case of hydrocarbon waste, the waste itself generated from nuclear power plants are themselves radioactive, right? And a lot of the waste material, a lot of the nuclei that make up the waste material have very long half-lives, right? So the question now becomes, how do we dispose of these, right? So there have been many issues dealing with that. Some years ago, there was a site in the Yucca Mountain of Nevada where it was suggested that we can dispose of those wastes. And pretty much, to be perfectly honest, different administrations basically, I don't know if it's I don't know what they're trying to do, but basically they pass on the issue to other administrations after their own. In some cases, they try to do something or they try to have meetings about it and so on, but nothing yet has been implemented. So things are basically at a stage where companies that generate their own waste are storing their own waste, but we don't know how long we can continue to do that. Okay, nuclear fission or fusion, which is basically the opposite of fission, is where you have two light nuclei coming together to form a heavier one, right? And this is particularly important because this is the reaction, or these are the types of reactions that are produced in the sun, right? So over 99.9% of the energy that reaches the earth comes from the sun. And these are the reactions that are responsible for the energy the sun generates. So the sun is basically a very huge nuclear reactor, which basically allow these reactions to take place, which produce energy in the form of radiant energy, and that's basically the energy that we are exposed to here. So scientists have been trying to recreate this on Earth, and this one attempt, and I don't know, to be perfectly honest, how far they have gotten as far as this is concerned, but basically what they were trying to do is basically bring the nuclei together so that the reaction will take place, right? The same nuclei that I showed you before. The problem with this particular process is that because the nuclei are positively charged, they will repel each other, right? So there's a huge energy cost which comes into play when you try to force these particles together, right? So at the front end requires a large amount of energy, but if you can succeed in overcoming the repulsive forces and get them to react, then the amount of energy produced after that would be greater, right? So that's basically the theory behind how this should work. And in this particular case, they basically have the ions in the form of a plasma gas. Plasma basically means ionic gases or gases made up of ions. And they have to be concentrated. So a lot of that requires energy, and you have to use a magnetic field as well in order to try to get these particles to collide. So the big drawback, as I said before, is the amount of energy that is required upfront before you can have any reaction taking place, right? There is, I remember about a couple of years ago, maybe 3-4 years ago, I came across a video, and how many of you guys know Neil deGrasse Tyson? Nobody? Oh, good, right. So he's one of my favorite persons because, let me see if I can find that video. I think I've probably stored it in the module section. He's one of my favorite persons because he has a very unique skill. And his skill is that he's able to explain science to the common man. A skill which I wish I had. Let's see here. Okay, let me see if I can find it. You know what? Let me do it over here so that students in Zoom can. Okay, let me see here. Okay, so. In fact, let me put his name. Okay, I think this is it, right, okay. Okay, you guys out there in Zoom, did you hear that?
Oh, the knows about saving money.
Can you hear it? Type of one if you could hear the volume. Let me play it again.
Everything I'm wearing, I've had since boot camp.
And I just saved on my car insurance for driving safe with USAA.
Insurance and license.
All right, so let me
So
skip
this will
this.
be a benchmark day. We'll look back on that fondly. But Chuck, what's been bugging you lately?
I'll tell you, I don't know if it's bugging me. Maybe I'm happy about it. Maybe the entire human race has something to be hopeful about. You know how I feel about climate and the climate crisis.
Right.
So I wake up this morning and it's all about fusion. Fusion everywhere. Everybody's talking about fusion. I'm like, whoa. Whoa, is this a good thing? Or are they yanking my chain? Are they just making me, what are they doing? Are they doing a Lucy pulling the football away from me? What are they doing? What is happening? What is happening with the fusion?
Oh, okay. So, the highlight is at one of the national laboratories, Lawrence Livermore National Laboratories, where they among all the national labs are one of their major tasks is as shepherds of our nuclear arsenal. Okay, the nuclear fuel, basically. So radioactive materials that might be used in weapons, and it is funded by the Department of Energy, not the Department of Defense. So that in fact, the total amount of money we spend on defense is not only the DoD's budget, but an important fraction of the Department of Energy's budget that involves weaponry, basically. Okay.
Right, yeah.
So there, they have the world's most powerful laser. And what they do with a bunch of these lasers is they aim them all at a tiny target and they cause the target to explode. All right, that
Okay.
okay, but
Sounds like America so far.
well, what's new about this? We've been blowing it up
Exactly.
like forever. So if the target is uniformly heated, evenly in all directions, and the material is very uniform in all directions, so there would be a spherical shape, then the explosion creates an implosion on the other side of that explosion, right? You can't just have stuff come out unless the Newton's law for every action is an equal and opposite reaction. So
Reaction.
explosion that comes out creates an explosion that points inward.
Okay.
Very high pressure and very high temperature. And under those conditions, you could take two atoms, light atoms,
Right.
and merge
Right.
them into a heavier atom.
Sweet.
That takes a lot of high temperature to accomplish. Because
Right.
let's take the lightest atom of them all, which is what?
I don't know, maybe hydrogen.
Hydrogen, you got it. So hydrogen in its nucleus has one proton.
Right.
And helium in its nucleus has two protons plus two neutrons. So how am I going to create a helium atom from a hydrogen atom? So you got to get a bunch of hydrogen atoms together. All right. Together. Well, here's what no one is telling you in the news, but it's obvious when you think about it. What do two protons want to normally do? They're both positive charge.
They like each other, but they don't like each other because they're alike.
Okay.
It's like when you meet somebody at a cocktail party and they remind you of yourself, and you're just like, I don't like that dude. I don't really like that. I don't want to be over there talking to that dude.
No, you're still in therapy, people, just so you know.
I know, exactly. So like, yeah, it's a simple question, Chuck. Where did cocktail parties and liking people come in? Yeah, but they want to get away from each other, right?
So these are like charges. So in the case of two protons, they repel each
Right.
other. So
Right.
how do you get them to come together as a new helium nucleus if they want to repel? So this is like rolling a ball up a hill, all right? If you don't give it enough energy, it's not going to reach the top. It's not going to reach the top, okay?
There you go. So, yeah.
If you roll it faster and faster, giving it more and more energy, eventually the ball will reach the top and tip and go over and fall on the other side of the hill.
Two ex-NASA engineers just created a portable AC that is making old expensive models obsolete. Power co-
That is
Right.
precisely what's going on with two protons. Here it goes. The two protons want to come near each other, but they repel. Let's boost the temperature, which speeds everything up. They get closer to each other before they repel. Boost the temperature some more. They get even closer. There is a magic temperature at which these protons will come close enough so that an entire new force operates. It would have to be a strong force in the nucleus to keep two protons together. In fact, the
That's
name
quantum love. That's called quantum love.
Where's that disco song? I remember Jungle Love. Remember Jungle Love? We know Quantum Love. Yeah, Quantum Love is like until you cross over the barrier, and then you're there. So
Wow.
when they cross that barrier, a strong force that operates in the nucleus takes over. It's one of the fundamental forces of nature, and it's called the strong nuclear force. There it is. Okay. What it's called. It is a very short range force. It only operates on scales as small as the nucleus itself. But
Wow.
you have to get there for it to grab a hold of you and make a new atom. That's why it takes high density, high pressure, and high temperature to overcome this.
All right, so
That is
I'm
thermo.
with you though.
That is thermonuclear fusion. Thermo is hot, nuclear is the nucleus,
Right.
fusion, they're bringing it together. It turns out that when you do that, your products have less mass than when you started with.
Whoa,
Oh my gosh, where did the mass go?
exactly.
E equals MC squared. My
energy.
So the mass on the one side of the equation, if you lose it, it manifests on the other side of the equation as energy.
There you go.
There it is. And so they
That's
managed,
music.
so at the Lawrence Livermore Laboratories using lasers. And by the way, led the world in lasers like for decades. In fact, people on the inside call it lasers, lasers, and lasers. Okay, Lawrence Livermore National Lab. Okay.
Lasers, lasers, and lasers.
Lasers, right? So anyhow, so they have managed to, you can add up how much energy it takes to turn on the lasers and fire them. And then look at how much energy comes out after you've done this. And they got 50% more energy out of this than the energy of the lasers that went into it.
That's amazing.
Amazing. First time that's
Wow.
ever happened.
Now that's an energy source now because you got more out than you got in, which is what I want to know. Which is so. What did it take? What would it be? What did it measure? Like, is there anything significant? And percentage wise, that's great. But like, what would it take to turn this into an
It
energy?
just broke even. That would be a magic stone unto itself, right? But the fact that they got 50% more energy out than they put in, it says, oh my gosh, we can get the physics to succeed. And for my money, I'm saying if the physics works, then it's just a matter of time before engineers, I got this. I got make something out of that. I got this. And so
That's amazing.
yeah, and so I very much look forward. There's a civilization pivoting on this.
Yeah.
And by the way, what I just described to you, the sun does every moment of its life. The problem over all these years, is, of course, we've known how to make fusion. We've known how to make fusion since what, 1949 or something? When the first fusion bombs were called hydrogen bombs. They're using hydrogen. That's what I just told you. It's two protons and merging hydrogen atoms nuclearly together. So we've known how to make fusion forever.
Right.
The challenge is not how do you make fusion, how do you control it?
Yeah, because you don't want the electric company having to move to a new city because there's no city left.
Right, exactly. So, while in America, we're really good at blowing stuff up. We're less good at controlling that explosion, right? So, the holy grail was, can we undergo fusion in a controlled way, where one day you might be able to throttle it, or contain it, or transport it, and we'll finally get, maybe, that ending scene in Back to the Future.
Right.
Here's your cue, Doc. It's your kids. And you remember how, and Marty says, but Doc, where are you gonna get the energy? There's no lightning bolt, and there's no room for, what are you gonna do? And remember what he does?
He dumps a bunch of trash. Into the flux capacitor, which is now powered by fusion.
It's Mr. Home Fusion, right? It was like a blender.
That's right.
He puts it in, and that undergoes nuclear fusion. And so one day, perhaps, we have fusion reactors in every car. And then you could
Wow.
there it is. So this
Wow,
will
that's
transform civilization. Even regardless of the carbon footprint that it doesn't have, it would transform civilization. But it also happens to not have a carbon footprint. So we could stave off this growth of fossil fuel burning and greenhouse gases, and we'll still have to recover from the damage we've already done, because a lot of the carbon dioxide got took into the oceans. And if you start removing it from the atmosphere, it begins to come out of the oceans, and it'll do that until it becomes equal again. So you gotta recover that. But it is the future. And just I tip my hat to the science physicists and engineers at the national labs. And this whole thing was important enough. It was a press conference announced by the Secretary of Energy. So, chomping at the bit.
So then it is good news.
Good news. I suspected accurately, yes.
All right.
And we've been at it for decades. Just thought I'd tell you that. And so this will be a benchmark day. With the first and second week of December in the year 2022. We'll look back on that.
Another day in December that will live not in infamy. What is it when it's a good thing?
Femi.
Just Femi.
All right, Chuck, we gotta end it there.
All right.
All right, but way more about fusion. That's another show. We'll talk about stars.
Yeah.
There's more. And why stars explode. All right. I'll leave a teaser here. You ready? Fusion, you get energy by combining little atoms. Fission, you get energy by splitting big atoms.
Okay.
But wait a minute. There's got to be some point in the middle where these two phenomena meet. What happens then? Therein are the seeds of the undoing of great massive stars in the universe. That's a whole other explaining we'll get to. Oh yeah, nuclear fusion in a nutshell. This has been yet another Star Talk Explainer. Great to have you join us, putting fusion back on the map. Chuck, always good to have you.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking.
Okay, so that's basically what they were talking about with respect to nuclear fission producing energy and the potential for it to be used. As you said before, who knows, an engineer might come up with a modification of that reaction so that it can be used to propel cars and so on. I was trying to look up some information because I know that there are nuclear reactors that are used to power submarines. And I'll look into it some more, but I'm not sure if nuclear fission is the way the energy is produced in those instances. So I'm going to look up that and then I'll post some information about that online so that you can have it to look at. So with that said, that's pretty much the end of this chapter and this course. I'm just going to leave that for you to read upon. Oh, I guess I need to hold on. What did I do? Oh. Okay. Okay. I'm going to leave the rest of the PowerPoint for you to read upon. The rest of it is talking about the applications of isotopes, radioactive isotopes in medicine, and a brief description about the effect that radiation can have on biological systems, human beings, and so on. And that's pretty much it. So I'll leave that for you to read. In terms of what's going to happen for the rest of the semester, I guess you'll be reviewing, materials from earlier. Let me just say, by way of announcement, I won't be able to come on campus tomorrow, so we can meet, or we will meet tomorrow online via Zoom, all right? But I'll be here next week, well, definitely for your test on Monday and subsequent to that, all right? So, any questions before we leave, or if you have a question?
What you don't want to use today to review?
We could do that. I have no problem with that. I have no problem. Yes, sir. Yes, ma'am. Sorry.
The test 3 is Monday.
Yes,
When is the final?
Thursday. Mhm.
And then when is chapter 8 assignment due?
Good question. Let me set up a Dropbox for that now. So, assignment 8. Okay, so today is the 30th. I'm gonna let it be due on Friday. August 1st. Okay, so it's due on August 1st at midnight. Yes, sir.
You know what the final will be structured like how many questions?
8 questions. Each question is based on a chapter.
Oh. And we had to answer all of them?
I'm sorry?
We had to answer all
Yeah.
of them?
Mhm. Okay, somebody has a question here? Oh, Miss Head, I think I just answered that question, right? Okay. Any other questions? Anything you want to review in the next 39 minutes? Yes, sir.
Maybe multiple parts per question.
Yeah, just like, the tests, and so on, yeah.
Guess we could do.
Oh, I'm sorry?
We can go first. Is it 75 minutes or is the whole?
No, the whole class period. In fact, I'll make it 2 hours just to.
I was gonna say, I guess we could do the questions on the final exam review, or the one for the past test.
And if I remember correctly, I published the answer key, right?
Yeah.
Well, let's see. Final exam, where is it?
It's under process.
That's key.
Oh, it's on the past test key. Okay, so yeah, we can go through this. Okay, so the first question, it gives you the solubility of sodium of carbon dioxide as 0.034 moles per liter. And the question is asking what is the solubility under atmospheric conditions? And it says here that the partial pressure of CO2 in air is 3.0 times 10 to the minus 4. So this is a Henry's law question, right? Henry's law is basically this equation right here. The solubility of a gas is equal to K multiplied by the pressure of the gas above the solution, all right? So the first thing we have to do is find out what K is. And basically, K would be equal to S divided by the pressure of the gas. They gave you the solubility, they gave you the atmosphere. So this is basically how you determine K. So it works so that K is equal to 0.034 M over ATM. Now the question is asking what is the solubility under atmospheric conditions, which means that the pressure of the carbon dioxide under those conditions would be 3.0 times 10 to the minus 4. So again, we'll be using the same equation, but this time we'll be multiplying the 0.034, which is K, by the pressure of the gas, which is 3.0 times 10 to the minus 4. And that's basically the setup here. All right, solubility is equal to 0.034 M over atmosphere multiplied by 3.0 times 10 to the minus 4 atmospheres. And that's pretty much it. You do the calculation and you get your answer rounded off to 2 sig figs in this case. All right? So that's pretty much how that is done. Any questions about that one? Yes, sir.
You have, for when you're solving for K, you divide it by 1 atmosphere.
Yeah.
And then, but is that for partial pressure?
That would be the pressure of the carbon dioxide. That would be the pressure of the carbon dioxide above the solution. The pressure of the gas is the gas over the solution. All right?
And then solubility would just be.
The concentration at that point, right? The molarity. And the concentration doesn't have to be expressed in molarity. It could be expressed in grams per whatever, per liter, whatever. All right, any other questions about this one? All right, now this one has to do with Raoult's law. It says how many grams of sucrose must be added to 552 grams of water to give a solution with a vapor pressure of 2.0 millimeters mercury, less than that of pure water at 20 degrees. And it gives you the vapor pressure of water at 20 degrees at 17.5 millimeters mercury. So the question says that the vapor pressure of the solution would be 2 millimeters mercury less than that of pure water, right? So basically to find the vapor pressure, let me see here. To find the vapor pressure of the solution, that would be equal to the vapor pressure of water minus 2.0 millimeters mercury. That gives you 15.5 millimeters mercury. And then now we use Raoult's law. So basically this is the equation for the vapor pressure of the solution, right? That would be equal to the mole fraction of water times the vapor pressure of pure water plus the mole fraction of the sucrose times the vapor pressure of the sucrose. Now the thing is, and I didn't write it here, the sucrose is a solid, right? And solids have a vapor pressure of 0, right? Because solids do not produce, the vast majority of solids do not produce vapors, right? There may be maybe 1 or 2 that I can think of right now, but sucrose is definitely not one of them, right? So basically this part here is going to be equal to 0. So basically this part here is going to be equal to 0. So therefore this simplifies the equation to get P of the solution. P of the solution is equal to this right here, right? So once we get that, then we can write down a relationship between the mole fraction of water as being equal to the vapor pressure of the solution divided by the vapor pressure of water, which we calculated here before. We calculated the vapor pressure of the solution, so that goes up top here, and we divide it by the vapor pressure of the pure water, and that gives you the mole fraction of water. And by definition, the mole fraction of water would be the number of moles of water divided by the sum of the number of moles of water and the sucrose. And basically from here is just algebra, because the question is asking for, let's go back up here, see what the question is there. The question is asking for how many grams of sucrose. Now, all we have to do from here is solve for the number of moles of sucrose. So a lot of algebraic manipulation will be required. So what you do here at this stage is multiply the 0.866 by this sum total here, and we end up with this, and that would be equal to the number of moles of water, which is this right here. And then what I did was that I distribute the 0.866 across what's present within the parentheses here. I end up with this, and then what did I do? I rearrange this to solve for the number of moles of water by subtracting the number of moles of water term here from both sides, and I end up with this equation right here. And then I rearrange this to get the number of moles of sucrose, and then I get that relationship here. Now, the question gives us the mass of the water. So basically what I did was divide the mass by the moles to get the, okay, I think something is off here. This should be the number of moles of sucrose. So let me correct that right here. So this here would be the number of moles of sucrose. 0.155 plus this here would be the moles of sucrose. Right?
Oh, so instead of grams, it should be.
Right, it should be moles of sucrose. So that means that this answer is not the final answer, because what we have to do next is multiply to get the mass of sucrose. We have to multiply the moles that we got here, which is 4.75 grams, by the molar mass of sucrose. Now, the formula of sucrose is hold on. Let me get the calculator out first. The molar mass of the sucrose is C12 H22O11, and that's the formula, so 342.3. So basically what you're going to do here is multiply this is moles, multiply 342.3 grams per mole, and that will give you the answer. So let's see what that gives. That would be 4.75 times 342.3, and that would be 1,630. Well, where are you? Okay, so this is going to be 1,630 grams of sucrose. All right, and that's how you do that.
Can we go back to like how you get the moles of H2O?
Well, basically, like I said, I did a lot of rearrangement here. Ultimately, I get the number of moles of
Or the 0.886.
Okay, hold on.
It looks like you get grams of water.
Let me check out something here. Well, here is where the moles of water comes in, because the question gave us the mass of water, right? So
Okay, so but first we solve for moles of water.
exactly, right here. And then we multiply, because remember, it's 0.155 times the number of moles of water. This is the moles of water. We multiply by 0.155, and that gives us the grams of sucrose. I mean, the moles of sucrose. Right?
Okay, hold on.
And then we do the rest. Then we multiply the moles of sucrose by the molar mass, and that gives us the grams.
I gotta backtrack. Okay, so what is the 0.886? Where we do the,
Okay, so the 0.886 comes from here. That's the mole fraction of water, right? So, and I set that to be equal to this here, number of moles of water divided by the sum of the moles of water and sucrose. And then what I did was that I multiplied this by this to get this here. And that would be equal to the number of moles of water. And then basically I rearrange it. I distribute this first to get this right here.
so you
right.
solve for moles of water using that equation, just rearrange.
Well, we solve for the moles of sucrose.
Moles of sucrose.
Right. That's this equation right here. And when I worked out this part, that's equal to 0.155. If you take 1 minus 0.866 divided by 0.866, that gives you 0.155. Then you multiply by the number of moles of water, which is this right here. And that gives us ultimately the moles of sucrose. And then I multiply that by the molar mass to get the grams of sucrose.
So we get moles of sucrose,
Mm-hmm.
and then we times it by the moles of water to get.
No, the molar mass, no. This is the moles of water right here. Oh, I guess what you're saying, right. The moles of sucrose, that is equal to 0.155 times the moles of water.
Yeah.
Right? So when we worked this out, we got 4.75 moles of the sucrose.
So that'd be the total moles of the solution, right?
No, just the sucrose. This part right here. We rearranged this equation, the number of moles of water equals to this right here. Right? We rearrange it to get the number of moles of sucrose, which is this right here. And that is equal to the number of moles of water times 1 minus 0.866 divided by 0.866.
Oh, okay.
This part here works out to be 0.155. And then you multiply that by the number of moles of water, which is this right here, and that gives you the moles of sucrose.
Okay,
And then you multiply it by the molar mass to get the grams of sucrose. Okay, any other questions about this one? Any other questions? Yes, sir.
The moles of water, multiplied by 1 minus
Okay, where are we?
on the right side,
Here?
a little bit above.
Here?
Yeah, right there. Is that just another way of rewriting 0.866 moles of water when you subtract it to that right side?
No, it gets on the bottom left. You cross multiply.
Yeah, I cross multiply, well, I started from here, right? I cross multiply the 0.866 times the bottom part here, and that will be equal to the number of moles of water. And that's how I end up with this equation right here, right? And then the aim is to get this by itself on one side of the equation, the number of moles of sucrose. So I distributed it to get this right here. And then what I did was that I subtract this term here from both sides, right? And I end up with 0.866 times the number of moles of sucrose is equal to the number of moles of water times 1 minus 0.866.
So in the original equation where it says 0.886, which is the
Mole fraction.
mole fraction,
Mhm.
the top in the numerator part, it should be, is there a different way to represent mole fraction? Because it just says moles of H2O over moles of H2O plus moles of sucrose. Like it's the same.
Well, this is by definition. This here is the definition of mole fraction. Because the definition of mole fraction is for one component in a system, the number of moles of that component divided by the sum moles of all the components in the mixture.
Okay.
So that relationship right here is by definition. This is basically not by definition, but it's true because of the previous equation that we had up here, right? So that's the definition here, and then of course I go through all the steps to get the moles of sucrose, and then multiply by the molar mass down here to get the mass of sucrose. All right. Okay, any other questions about this one, or shall we move on?
Yeah, I think I understand.
All right, let me clear this here. Scroll down. Okay, so this question is asking for you to calculate the molarity of a solution made up of 30.0 grams of ammonia in 70.0 grams of water, and it gives you the density of the solution as being equal to 0.982 grams per mil, right? So the approach that I took here is that by definition, the molarity is the number of moles present of a solute in 1 liter of solution, right? So what I did was assume that, okay, let's start off with 1 liter of solution. And then based on that 1 liter, whatever the moles that we work out to get, that would be the molarity, right? So I start off with 1 liter of solution, I convert that to mils, right? Now, because the density is 0.982 grams, we can find out what the mass of the solution present in 1 liter, and that's where we multiply the 0.982 grams by, this should be 1 mil of solution. So that's another error right there. So let me correct that. So this should be 1 mil. Right? I think the answer works out to be what it should be anyway, but that should be 1 mil, right? So the liter units will cancel out here and here. The milliliter units will cancel out here and here, right? So up to this point, we have the grams of the solution. Now the question says that the solution itself, 30 grams of which would be ammonia and 70 grams would be water. So therefore it's a 30% solution of ammonia. So that's what this conversion factor represents. 30 grams of ammonia divided by 100 grams of solution, and that will give you the mass of ammonia present. The grams of solution will cancel out. And then the next step is to convert the mass of the solution in grams to moles. The molar mass of ammonia is 17.03. So we divide the 30.0 by the 17.03, and we end up with 17.3 mils. Let me just make sure that this is correct. I'm very sure it's correct. Times 0.982 times 30 divided by 100 divided by 117.03. Right, so the final answer is 17.3 moles. So therefore, for every 1 liter of the solution, the amount of moles present of the ammonia is 17.3 moles. So therefore, we can conclude that the molarity is 17.3 m. All right? So that's basically how that is done. Any questions about this one? Any questions? Any questions? All right, so let me scroll down. Okay, this one is a typical rate law type of question. They gave you the table with the data, right? They gave you the reaction, they gave you the concentrations and the rate of disappearance. So the question is asking for us to do what? Wait a minute. Oh, okay, so the first question is to determine the order of the reaction with respect to X and Y. So basically, I just write down a general equation where I raise the concentration of X to M and the concentration of Y to N. M and N, of course, would be the orders of the reactions with respect to X and Y respectively. Key thing you need to remember when you're doing these problems, make sure that you choose 2 sets of data where the concentration of one reactant is constant and the concentration of the other reactant changes. Right, that's the key thing. So what I did was I chose this set of data here and this set of data right here, because between these two, the concentration of Y doesn't change, but the concentration of X changes, right? So by so doing, we can find out the order of the reaction with respect to X. So basically, I set up the equation 1.02 goes here is equal to K times the concentration of M of X, which is 0.4, times the concentration of Y, which is 0.6, and then I do a similar thing for this set of data right here. I plug in these numbers into the same equation, and I end up with this. And then what I do next is cancel out what can be canceled out, which in this case would be the 0.6 here and here. The K's will cancel out and the units will cancel out. So you'll be left with this. And then you're gonna divide the 1.02 by the 0.254, you get 4.02. This divided by this will give you 2, so therefore M works out to be 2. So the order of the reaction with respect to X is going to be 2. And then we do something similar. This time we choose 2 sets of data where the concentration of Y changes. So the sets of data that we choose in this case would be this one here and this one. Y changes, but X remains the same. So when I did the same thing and plug the numbers in, right, I end up with this right here. After doing the cancellations and all that, I end up with 2 is equal to 2 to the n, which means that n is equal to 1, right? So therefore, the order of the reaction with respect to Y is 1. So therefore, the rate law is what I have down here. Rate is equal to K times X raised to the 2 times the concentration of Y raised to the 1. And that's the rate law. The question didn't ask for the rate law, but if the question did ask for it, then that's what you'd put, all right? The question only asks for the orders of the reactions, right? So this question now, B part is asking for the rate of disappearance of X when the concentration of X is 0.30 M and that of Y is 0.40. So basically what you need to do is rearrange this. Oh, wait a minute. Oh, we needed to find a rate constant first, right? So K, the question didn't ask for that initially, so we need to find a rate constant first. So basically you can choose any set of data and plug the numbers in to get the rate constant. I think I choose the first set of data and I plug them into this equation and I got this as a rate constant. And then to get what the question is asking for, which is a rate when the concentration of X is this and the concentration of Y is this, I plug these numbers into the original rate law using the rate constant, which we calculated here. And then we do the number crunching and we end up with your answer as 0.40 M over S. And that's basically it. All right, any questions about this one? Any questions?
And the only values of like M and N are gonna be 0, 1, 2.
Right, 0, 1, and 2. You won't get any more complicated than that, right? All right, so if you get something otherwise, something is wrong. Okay, any other questions? Any other questions? Okay, scrolling down. This is an equilibrium constant type problem. They gave you, this should be 2 arrows. But anyway, they gave you the equation, they gave you the Kc, and the question says calculate the equilibrium partial pressure of all the components starting with pure phosgene, which is this, at 0.760 atmospheres. So basically, this is the ice table. You're gonna start off with the initial amount of phosgene being 0.760. The initial concentration or pressure, I should say, of carbon monoxide is 0 and 0. The change for this would be minus X, plus X here, plus X here. You're going to end up with these values or these terms, and then you're going to plug the values into this expression, and you're going to end up with this right here. And again, algebra will be involved. In this particular case, you're going to end up with a quadratic equation, right? And again, if you haven't done so before, I don't imagine why, but make sure that your calculators that you're going to use is set up to solve quadratic formulas. That would help in terms of, you being able to do these questions more quickly. In this particular case, the 2 values of X are these 2. You'll notice that one is negative, so we can kick that one out because that is not applicable to this situation. So once we determine X here, then basically we can determine the pressures of the gases based on the terms in this equation right here. So in the case of the carbon monoxide and chlorine, X would be equal to 0.0571. And in the case of PCO2, COCO2, the pressure is equal to 0.760 minus 0.0571. And that gives you 0.703 atmospheres, right? Now, I just realized also that the question is asking not for the pressures. Oh, yes, it does. Okay, my bad.
And not concentration.
Yeah, not concentration. They're asking for the pressure. Okay.
And could you do the, like where you do the percent association, the 5% rule on this or no?
Could work because, and the only reason why I said that is because the K value is small. So yeah, you could do that. And check to make sure that it's valid and all that. It wouldn't work if it's large though. If KC is large,
Yeah.
then you'd have to just go through the steps. Okay. So the next question is saying, to the left, which means that the concentration, okay, what's going on here? Okay, I don't know. Something is going on with the
Share the screen.
share, yes, for some reason. Okay, sorry about that, you guys over there in Zoom. So as I was saying, the equilibrium position will shift to the left, which means that the concentration of the reactant COCl2 would increase, while those of carbon monoxide and chlorine will decrease. So please note the question says, explain the changes in the concentration of all of these, right? So you have to explain which one will increase and which one will decrease and all that good stuff. Okay, the next one is temperature increase. So what do we look for when it comes to changes in temperature in order to make the prediction as to whether or not the reaction will shift? Exactly. So you're going to see whether or not the reaction is exo and endothermic. And this reaction here is endothermic, right? So therefore, if you increase the temperature, which direction will the equilibrium position shift to? Will it shift to the right or will it shift to the left? Will it shift to the right. So therefore, the concentrations of the carbon monoxide and chlorine would increase, and the concentration of the COCl2 will decrease, all right? And then the last one is easy. When you add a catalyst, what will happen? Nothing, right? Because the rate of forward and reverse reaction would increase to the same extent, so therefore there will be no change in the equilibrium position. Let me remind you that when it comes to the effect on the equilibrium constant, the only factor that will change the equilibrium constant is temperature, right? Constant, Kc, Kp, whatever the K is, right? The only factor that changes the equilibrium constant is temperature, right? If you change the concentrations and then it restores equilibrium, the Kc value will be the same, all right? Same is true if you change pressure, but temperature, if you change the temperature, the Kc will be affected. So like, for example, in the question that we just looked at, we said that the equilibrium will shift to the right. So that means that you have more products than reactants compared to what was before, which means that the Kc value would increase, right? So you could be asked a question where, it could be a bit of a trick question. What would happen when you increase the pressure? What would happen to the Kc when you increase the pressure? The answer is nothing, right? Well, what would happen when you increase the temperature? Then something would happen. Kc would either increase or decrease, depending on whether or not the reaction is exothermic or endothermic. So you have to be careful when it comes to, those kind of questions. Okay, this one here.
Wait, so Professor?
Oh, I'm sorry. Yes, sir.
For this example then, since it's endothermic and temperature is increasing, does that mean the Kc is gonna increase as a result?
You mean Kc?
Yeah.
Yeah. Because it's going to shift to the right, which means that the product will increase, the concentration of the reactants will decrease, which means that Kc would increase. or KP, or whatever the K is. All right, okay, I don't know if we'll be able to go through this completely in the 8 minutes we have left, but in this case here, the question says calculate the pH of the following solutions, right? And the first one is 0.36 m sodium acetate. That's what this is, right? So first thing you need to recognize is that sodium acetate will dissociate completely. So NaA will undergo complete dissociation to form Na plus A minus, right? And it's an A minus now, being a conjugate base, will react with water to form hydroxide ions, right? So, of course, what I did first is set up the ice table, right? Ultimately, you're going to end up with this line right here. And then we're going to plug in the terms into this equation. You're going to end up with this. The thing is, we don't know what Kb is because you won't see Kb in the tables that I'll provide for you for the acetate ion, but there will be the Ka for the acetic acid. So that's why Kb will be equal to 1.00 times 10 to the minus 14 divided by the Ka for the acetic acid. And that will give you the Kb for the acetate ion, right? So once we get that, we make an assumption that X is small compared to 0.36 such that this denominator reduces to 0.36. And then we go ahead and solve based on that. And I end up with X being equal to 1.4 times 10 to the minus 5. Of course, you have to find the percent dissociation to make sure that the assumption is valid. When I did that, I got 3.9 times 10 to the minus 3%. So of course, that's valid because it's less than 5%. So therefore, we can go ahead with X being equal to this, and X will be equal to the concentration of the base. So to find the pH, we find the pOH first. When I did that, I got 4.85, which is minus log of 1.4 times 10 to the minus 5. And then, of course, to find the pH, I subtract 4.85 from 14, and that gives you your pH, and that's it. All right, so that's basically how you do that. And I don't remember if I said this in class, but I do remember saying it to at least one person. When you're doing these questions, don't just go through the steps blindly, because, for example, in this question, before I even start the calculation, I can tell that the pH is going to be greater than 7, right? So I remember, in fact, if I remember correctly, I did one example and I got the answer wrong, and I knew the answer was wrong because the pH was less than 7.
Yeah,
So right, and then I had to go back and correct it. So yeah, you have to, when you're doing these questions, just think about what you're doing, see if the answer makes sense, because like in this case, you know that the pH will be greater than 7, and then when you do the problem, then you see that the pH is actually greater than 7. All right, I'm going to stop here. We can continue this, or if you have any other questions, in terms of review. So basically, it's review all the way until the final. We can review tomorrow for your test number 3, and then after that, we can review for your finals, right? So remember, I won't be here. This will be done online, all right? So don't waste your time coming up here if you don't have to. Okay, and for you guys out there in Zoom, I will be signing off